Okay, so this is the continuation for our lesson in chemical kinetics. The objectives of today's video is to be able to calculate for the average reaction rate when you're given the concentration of either the reactant or the product. Also, you should be able to relate the reaction rates of the reactants and products using stoichiometry. So, if you can recall, we have already defined what reaction rate is. And it's actually the speed of your reaction as time progresses. And then, the reaction rate is calculated as the change of concentration over time. So, if you can imagine, right, when you have a reaction, you start with the reactant and end up with a product. So, if we can actually graph the concentration of our reactant over time, we would expect the concentration to decrease because it's being consumed. The reverse is true for the product. Over time, we would expect the amount of the product to increase as more and more reactant is converted into products. And so, the reaction rate is the change. Now, in mathematics, we designate or denote change as delta. So the rate can be written in mathematical terms as the change in product concentration. So in chemistry, we use bracket to denote that this is the concentration. So this right here is read as the change in concentration of the product over time. So since this is change, just like in your physics lesson about speed or velocity, change is calculated by subtracting the final and the initial quantities. So the change in product concentration is just the difference of your final and initial concentrations of the product over change in time. In the same way, we could also express rate in terms of reactant concentration. So still you would have final minus initial. But you might have observed, class, that you have the negative sign here. Okay. This should have a negative sign here. Now, the negative sign is just for us to have an overall positive value. Note that we have shown in the graph that the concentration of the reactants would decrease over time. So the quantity final minus initial concentration, if we're talking about reactants, would be a negative value. So to do away with that negative value for the rate, we just add a negative sign. So that overall, the rate, whether we are calculating it based on the product amount or the reactant amount, would be a positive value. So for the product, it's final minus initial, and then for the reactant amounts, you have still final minus initial, but we add a negative sign to do away with that negative quantity. Okay. Also, the reaction rate, its units is in terms of concentration over time. So if you can recall in our lesson about concentration expressions, we had the molarity there. So the typical unit for reaction rate would be in terms of molar per second, okay, or mole per liter per second. And just like in your physics class wherein you discussed about instantaneous speed, or that's the particular speed at that instant, we also have a term instantaneous rate in chemistry. So instantaneous rate is the rate of the reaction at that given time. Okay, so let's have a sample exercise. Okay, so you have experimental data for the reaction of bromine gas and methanoic acid to form hydrogen bromide and carbon dioxide. So for this particular reaction, we have this data. So we have the initial and final time. we were also able or were given the initial and final concentrations of our reactants, bromine and methanoic acid, as well as one of the products, hydrogen bromide. So for the question, we are asked to calculate the average reaction rate over 1/52nd expressed in terms of the disappearance of bromine, and for B, still the reaction rate over 1/52nd, but we're going to calculate it in terms of the appearance of the product hydrogen bromide. So let's answer letter A. So for letter A, you have disappearance of the reactant bromine. So we have the negative sign here. And then we substitute. You have the final and the initial quantities over our time interval. If we input that in the calculator, okay, you have to input it in practice at home, then you would get 3.27 times 10 to the negative 5 molar per second. Okay, so the reaction rate, or we could also say that bromine gas disappears at the rate of 3.27 times 10 to the negative 5 molar per second. Now for letter B, calculating in terms of the appearance of hydrogen bromide, you have this equation, okay? And then still change for delta is final minus initial quantities for HBr. So you have these over 150 seconds, and then if you input it in the calculator, you should get these values, 6.53 times 10 to the negative 5 molar per second. So the product, hydrogen bromide, is actually appearing at this rate. Okay. Now, let us look at the answers we found for letters A and B. As you can see here, these numbers are all related to one particular reaction, but the rates of disappearance and appearance, particularly the rate of disappearance of our reactant bromine and the rate of appearance of the product hydrogen bromide, are different. Okay, can that be true can we have different rates of disappearance and appearance for the same reaction? If you look at the values, you would actually observe that the hydrogen bromide's rate is twice as that of the bromine's reaction rate. So we could say that the hydrogen bromide is formed twice as fast as the bromine being consumed. But how can we relate these two values pertaining to the same reaction, but we have different rates for the product and for the reactant? Why they are different is because of stoichiometry. So actually, the rate of disappearance of a reactant and the rate of appearance of a product can be different from each other, or they can have different values. And they can have different values just as our example because of stoichiometry. So recall that this is our balanced equation, and these are our calculated values. Now, how can we calculate, or how can we relate these, aside from noticing that when you multiply this one by 2, you would get this? Okay. So let's try to derive from the rate of disappearance of bromine. Can we go to this one, to this other value using stoichiometry? Okay, so we take this term here, or this value here. Now, if we are going to take apart the component units of the molar unit, we can actually form mole per liter, right? Recall our concentration expression lesson. So molar is just mole per liter. And since this value is pertaining to bromine, we just affix the formula for bromine. And then, recall our discussion on stoichiometry. We can relate the amounts of each chemical involved in the reaction through their coefficient. So if we convert bromine into HBr, we would have this conversion factor. 2 moles of hydrogen bromide is formed per 1 mole of bromine gas. After which, we can now get this remaining units. Okay. And if we do the math, you can actually get 6.53 times 10 to the negative 5. And the new unit would be mole HBr per liter per second. So actually, for the previous lesson, we could have solved letter B using the values of using the answer that we got from letter A, using stoichiometry. Okay. So let's move forward to another sample exercise or sample problem, which you should try doing on your own. Ozone gas decomposes into oxygen gas given the balanced equation below. If the rate of appearance of oxygen is 6 times 10 to the negative 5 molar per second at a particular instant, what is the value of the rate of disappearance of ozone at this time? So this is the balanced equation. If you can recall, ozone is found in the ozone layer in our atmosphere, and it's the one responsible for blocking the harmful UV radiations from the sun. So you should try doing this. You can pause the video and try doing it on your own. And once you're done, you should get this answer. You should get an answer of 4 times 10 to the negative 5 molar per second.